Hey guys, welcome back. It's time for Chapter 7, Internal Energy. I want to begin by reviewing a little bit about elastic potential energy. If you start with Hooke's law, which says that if you compress or stretch a spring, you get a force that goes like minus the amount of compression or stretch times a constant, and you go to compute the potential energy stored in the spring, that would be the integral of minus the force dotted into the displacement. Remember, the force is minus the derivative of the potential energy, so the potential energy is minus the integral of the force. You could think of it that way. You end up with a potential energy that's related to the stretch, and it looks like a quadratic. Now this is only valid, the quadratic part is only valid for very small amounts of stretch, relatively tiny compressions or stretches. But it's a good model as long as the stretch isn't too much. You can relate this to the bond strength of two atoms that are near one another. It turns out that for small amounts of stretch, the work needed to separate or push the atoms together also looks like a quadratic for exactly the same reason. Now, folks who are interested in this use a slightly more sophisticated potential to model actual neutral atom interactions. It's called the Morse potential, and it does a pretty good job of approximating the potential energy as a function of separation for two neutral atoms. It kind of looks like this. It has a minimum. That's the equilibrium separation between the two atoms. And if you try to separate the atoms farther, you have to do work, so the potential energy goes up. If you try to push them closer together, you have to do work that way as well, so the potential energy goes up. So it has a vague resemblance to the quadratic potential. In fact, at the minimum, the resemblance is quite good, and that's basically what we're going to do, is assume that we're close to the minimum, and so we can use the quadratic approximation both for two atoms that are interacting with one another and also for a collection of atoms, because remember, a collection of atoms, kind of like a collection of springs, also has the Hooke's law behavior. Now, in this chapter, we're also going to be dealing with thermal energy, and thermal energy is really just microscopic kinetic and potential energy, and the average kinetic energy and potential energy per atom, I'm being vague here because it's not exactly right. We'll get a better definition of temperature later, but the temperature is kind of like the average kinetic energy per atom or per molecule. The specific heat capacity is a proportionality constant between the change in temperature and an amount of thermal energy needed to produce that change in temperature. Specific heat capacity is heat capacity per unit mass. So to get the change in the amount of thermal energy needed to produce a change in temperature, you take the mass of the thing times the specific heat capacity times the change in temperature, and you get the thermal energy needed to produce that change in temperature. If you followed that, you'll know that the specific heat capacity has to have units of joules per gram or per kilogram, and then per degree Kelvin or per degree Celsius. So that's the idea of specific heat capacity. We'll work a problem here in a minute that shows kind of how that works. Also, we're going to add another term to our energy principle, which we talked about in class, but I just want to point it out here. It has to do with energy transfer due to temperature difference. If there's a temperature difference between the system and the surroundings, you'll get a thermal energy transfer, and that thermal energy transfer corresponds to a change in temperature. So as the temperature goes up, and this is the formula for specific heat capacity, mass, change in temperature, and the amount of thermal energy needed to do that. So one other new idea in this chapter is the concept of power. Power is the rate at which energy changes or flows. Energy moves from place to place or from form to form via work and or heat transfer or thermal energy transfer. I'm going to try to use heat as a verb whenever I can, but I'll probably forget sometimes and say heat as a noun. But basically, when thermal energy goes from place to place, then that can be thought of as a Q in our equation, delta E equals work plus Q, and power is simply the rate at which energy flows, so the rate in time. So a watt is a new unit, which is 1 joule every second, and that's a unit of power. So finally, or at least not finally, but next is the idea of dissipation. So dissipation is a process, usually it's involving work of some kind, in which energy changes from organized macroscopic energy into microscopic potential and kinetic energy, usually associated with thermal energy. So friction is an example, where if you've got sliding friction, where two objects slide against one another, the interface between those two objects generally gets warmer, increases its temperature, because friction involves a lot of little tiny motions, and those little tiny motions correspond to microscopic kinetic and potential energy, and we interpret that as thermal energy, which basically involves changes of temperature. Air friction is another example of dissipation, which results in change in temperature, and another case where you end up getting dissipation and changes in temperature is electrical resistance, which we'll talk more about next semester. So we have a couple of approximate models that we use for friction and drag. There's the air drag, quadratic air drag formula we'll be using in the lab on Monday, where we drop the coffee filters and estimate the air drag force acting on the coffee filters. We're going to find that it's proportional to their velocity squared, for reasons that we may get a chance to talk about on Monday. But also there's sliding friction, when two objects slide against one another. We've run into that before, and so you should be familiar with it. And of course there's static friction, where two objects are in contact but they're not actually sliding. So there's a frictional force associated with that contact, and but there's no work done because things aren't actually moving or sliding. There's no dissipative work done. So here was one of the warm-up problems that we had today, and people were so confused by it that I thought it would be worth actually working through it step by step. And so the idea is you have a block of aluminum that slides to rest on a rough surface, and we want to compute the increase in temperature of the block of aluminum. So the way I approached this was to do the problem twice. First, start with the energy principle and choose to make the block the system, where by the block I mean I'm going to ignore the internal energy of the block. I'm just going to keep track of the kinetic energy and nothing else. So the change in the energy that I'm going to bother to keep track of is simply the change in kinetic energy, and the work done by the surroundings will be equal to the change in the kinetic energy. Now the block and the rest of the surroundings are at the same temperature, so there's no Q at this point. And we simply write down that the change in the kinetic energy is equal to the work done by the surroundings. We can put in the numbers from the problem to get the work done by the surroundings. It turns out to be -0.4 of a joule. So that's one approach to the problem. Of course, that doesn't tell us anything about the change in temperature of the block. So let's work the problem again, but this time let's assume that the block and the floor and the surface and everything with it are the system, and the surroundings are everything else. But the point is, the surroundings don't exert any forces on the block that aren't negligible, and so the work done by the surroundings is going to be 0. And the change in the energy of the block has got to be the system. The change in the energy of the system has got to be 0. Remember, though, now the system is the block plus the floor, and the internal energy of the block is going to have to be included. So the idea is the change in kinetic energy we know is -0.4 joules. What else goes in there? And the answer is it's got to be the thermal energy that gets generated and that winds up in the block and the floor. The sum of those two guys has to be 0. Well, we know the change in kinetic energy is -0.4 joules. That means the change in the thermal energy has to be +0.4 joules. And if you go back and look at the text of the problem, you'll remember that I said that half of the generated thermal energy goes into the block. So that means that the change in thermal energy of the block itself is 0.2 of a joule. We can presume that the remainder of the thermal energy went into the floor, went into the surface. The surface of the floor warmed up a little bit. But the idea is that mc delta T is 0.2 joules. I can use that relationship, that the thermal energy produces a change in temperature of the block, to solve for the change in temperature, and it works out to be about 1,000th of a degree Kelvin. So that's kind of how you think about problems like this. Let's look at another one. A vertical spring with a certain spring constant is compressed, and a 50 gram mass, a 0.05 kilogram mass, is placed on top of the spring and released. How high will the mass rise before it reaches its maximum height? That's the question. So let's see what happens. We release the spring, the mass goes up, reaches some maximum height. S is the amount the spring is stretched. H is the change in the y coordinate of the ball. And how do we figure out how this works? Well, again, we use the energy principle. Again, we let the system be the ball plus the spring plus the earth. And the reason for doing that is that then the work done on the system by the surroundings is 0, and we simply have that the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy, all that has to add up to 0. Now at the beginning the ball's at rest, and at the end the ball's at rest, so the change in kinetic energy has got to be 0. The change in the gravitational potential energy is, in the relative gravitational potential energy, is mgh, right? And the change in the elastic potential energy, again, it's a relative elastic potential energy since we set it to 0 when S is equal to 0, then it turns out to be negative 1/2 ks squared. So the idea is the gravitational potential energy is increasing by mgh, the elastic potential energy is decreasing by 1/2 ks squared, and so the sum of those two has to be 0 because there's no work being done by the surroundings. So what you can do then is, I guess we'll watch it again here. What you can do then is solve that for the height, and it turns out the height is ks squared over 2mg. You can plug in the numbers, and you get 0.41 meters. So that's kind of how you can solve problems where it's all springs and gravity and kinetic energy and stuff like that, and you can apply the energy principle in a lot of cases like this. So I want you to try this out yourself, check it, and make sure you can do it, and we'll see you guys next time.